A common external flow is fluid motion cross cylinders that we would like to evaluate the convective heat transfer coefficient. Let's assume we have this cylinder that is in the main stream of a flow with the uniform velocity of, let's assume, u infinity that is passing this fluid. So what we would see here is as the flow coming and passing the cylinder, there is a formation of boundary layer. So we would have this fluid stream forming a boundary layer, and there is a point that this boundary layer separates from the cylinder, and it's because of the pressure gradient, adverse pressure gradients that happens. So these are flow stream around this cylinder. There is a point that the flow stream becomes at rest, and that's what we call stagnation point. And at this point, the velocity is going to be 0. Now, what happens here is as the flow comes and across the cylinder, what we are going to observe is an increase in the velocity, accelerating of velocity, because the pressure gradient is negative. So I put this one as x. The pressure gradient is negative, the flow accelerates. And it reached to a maximum when the pressure gradients become 0, and after that the pressure gradient becomes positive, which is adverse against the flow. And there is some point that the fluid velocity gradient, the velocity gradient at the locations becomes 0, and the fluid losses its momentum to counteract the adverse pressure gradient, and then the separation of boundary layer happen. So if I just exaggerate this cylinder and plot view velocity profile across this cylinder, so let's say this is the boundary layer that is forming here. At some point it's going to just detach from the cylinder. So this is the point that the velocity is just accelerating. So let's say this is u infinity of x. So remember that x and this u infinity of x is going to be a function of x. So it's going to change actually across the system. So the velocity is keep increasing till a point that we have dp dx negative. It is favorable velocity gradient. And in this zone, this is where we have acceleration of fluid velocity. Now, beyond that point, what we are going to see is, this is, let's say, dp dy dp dx is greater than 0. You're going to see adverse pressure gradient. So we see starting of fluid deceleration here, infinity of x. And there is a certain point that what we see is, if I make a plot of velocity gradient, you're going to see this is velocity profile, but what we have here is du dy is going to be 0. So that's what we call the separation point. And what happens if I plot another velocity profile here? What we are going to see is a reverse flow. So we have here what we call flow reversal, and we have a backflow actually, or you can call it backflow that happens. And then what we are going to observe here is the formation of these vortices, and you're going to see wake here. So this is the event that happens for the for the velocity profile and the boundary layer that happens across this cylinder. At the separation point is the critical adverse pressure gradient. So that happens at some critical adverse pressure gradient. Now, this has become important for the evaluation of heat transfer coefficients or measurement of heat transfer coefficient. And for the two cases of laminar and turbulent, we are going to see a little differences in the separation point. So let's say if we have a laminar case and there is this uniform flow, and what we are going to observe is the stagnation point, formation of this boundary layer. And you know, separation is going to happen somewhere much earlier than what you're going to see in a turbulent flow. So this is the place that separations happens. And if I have similar case, but in a turbulent regime, the boundary layer stays there up to about 140 degrees, and then you're going to see these separations happens. So if I find the degree here, the degree that the separation happened, this is the laminar boundary layer, and this is turbulent boundary layer. The separation point here happens around 80, and this one theta happens around 140 degree. Just degree, the angle of that one. And if you look at drag coefficient, CD here is 1.2, that's the drag coefficient. And CD here is 0.3. So these are the differences. Now there is a critical Reynolds number. For the cylinder that shows the transition. And that's based on the diameter of cylinder, RED, rho UD over mu, which is 2 times 10 to power 5.